Before we start on actual problems, I want to show you something. You've seen this website before, Gapminder, at least some of you? No, some of you haven't. But some of you have. I know that because I was talking to some other students and they've seen it before. Maybe not very many people in here. Okay, interesting. If you take data management, or it might be too late if you're already taking it, or if you are taking any kind of social studies kind of course or anything like that, this can be a very, very powerful website. This is actually the older version of it, so the newer version looks a little bit different, but either way, it does the same thing. It's interesting just to play with, but if you are actually studying anything like this, I mean, this could be a hugely powerful tool as a student to do a project or something like that. And like I say, it's also just really interesting. Came out a long time ago. There's a really neat TED video about it. The guy who created it, or at least had a big hand in creating it. And the neat thing about it is when you click on, so this is like a graph, obviously, and there's my vertical axis, and there's my horizontal axis. But when I click on the vertical axis, look at all the things that I can make it represent. So under economy, there's all these subgroups, and then under that, there's like a whole ton, like there's tons and tons of things that you can explore. Under all the subheadings, there's a whole bunch of options, and what you get depends on the data available. So some things, look interesting, and then when you click it, there's not that much data on it, but you can explore and you can go in there and you can look at different things. And some of them are incredibly telling, like really paint a picture with just a visual. In fact, it's not the point of today really, but it certainly does highlight the effectiveness of a graph. How much information, how much data can be shown with a graph. So there's, and it's, for this, it's more than just the X and the Y axes. Okay, so we've got those, and those are really important. In this case, the horizontal axis is income per person, adjusted for inflation, that's going to be important, and life expectancy. Okay, so that's what we're looking at. But the dots themselves have information embedded in them. So in this case, the colors correspond to a part of the world. Okay, and so you can see that yellow is the Americas, and orange is like Europe and some of Asia, and then red is more other parts of Asia. Green and blue are like different parts of Africa, Northern Africa, and then Central and Southern Africa, and so on and so forth. And then the size of the dot is population size. So when you're looking at those dots, just based on the size of them, what would you guess is the different dots? And then the other thing that you can't see, unfortunately, just because the projector is it's got the year embedded in the background. You can kind of see down here where the year is, but it says 1973. I can see it on my computer very well. For some reason, it's not showing up on the projector. And then when you hit play down here, what it's going to do is going to animate the change in all of these things over time. So the year is going to increase. Again, you're not going to see that, but you'll see the dots moving a little bit. So anybody have a guess at what that big yellow dot would be? What's a big country in the Americas that has a large population? Back in 1973, it was one of the biggest in the world. Yeah. So that's the U.S. Hiding usually close to U.S. Another yellow dot that's quite a bit smaller is Canada. So there's us. You can click on it. If you click on it, it'll highlight it. Okay, and I think it'll like follow it. It'll actually sort of paint the course of Canada. So you can do that as well. I'll post a link to this. My guess, usually China looks a lot bigger. My guess is this one's China. I don't know what this one is, Japan. That's something wrong with that, because back in 1973, I don't think they were that small, but maybe they were. And then this blue dot right here that looks kind of big is probably India. Okay, and you'll see, maybe back then they weren't that big, but you're going to see in 20 years, those two dots are going to explode in size, because we know that India and China are two of the biggest ones. And so What's interesting, here, let's play this and see what happens. So this is changing over time. I don't know. Look at that. Oh my gosh, look at the size of China, right? That's what I said. Holy cow. So, I don't know. Like, anything interesting happening there? Did the way the dots moved, where they went, where they started, where they went, did that mean anything to you? I don't know. It's kind of hard to tell. Like, we can play it again. I'll go back a little bit further. Depending on the things that you pick, the data will go back a long way or not. Like, sometimes it goes back to the 50s. In this case, it goes back all the way to 1800. But if I go back that far, there'll be like 2 dots because most countries weren't keeping data back then. But apparently a few were. So, for example, yeah, the UK was one of them. I can't even see what that is. Poland apparently had some data. Germany, oh, Canada, look at that. And the United States. So there's like 5 countries that had data dating back to then of life expectancy versus income per person. So the income per person was somewhere below 5,000. Okay, that's yearly, I'm sure. And again, that's adjusted for inflation. And then the life expectancy was below 40 for all 5 of those countries back in the 1800s, right? So when I hit, whoa, shoot, something's going on with, okay, let's try again. Hit play. I mean, they just kind of dance around a little bit, jumping up and down, not very interesting. 1830, 1840, there's more countries are popping in to existence. 1870, 1880, 1900s. But like, I don't know, there's not much of a trend, don't you agree? Like, so they're kind of all creeping up the edge here. All of a sudden, income per person is getting bigger. Who the heck is that? Look at that. Oh my gosh. That's like Qatar or something like that probably. Anyway, not very interesting. Or maybe it is. I don't know. Maybe you can see something happening there. What is interesting? The other thing that Gapminder can do, and the new version can do this too, it's a little bit more hidden. Not really, but a little bit more. But look at this. What does that mean? That little thing right there. Or this right here. It means it's a linear scale. So look at the scale. This is something we talked a lot about. You talked about it probably in elementary school. We talked about it a lot in grade 9, and then it doesn't come up too much after that. But like the importance of a scale, of the scale you choose when you're making a graph, what it means of reading it, that kind of thing. So take a look. 10,000, 20,000, 30,000, 40,000, 50,000, 60,000, 70,000. It's linear, right? And over here, 5, 10, 15, 20, 25, it's going up by 5s. And we teach you that that's the right way to make a scale. But it turns out, once you get into more interesting real-life applications of looking for relationships and that sort of thing, is we start to play with the scale, and we do things like we make it logarithmic. I'm not going to know which one's the right one to make logarithmic. Nope, that's not right. So I'm going to try this one, okay? And then what happens back in 1900 is you get a little bit more of like a graph. See what I mean? Like it's not huddled up the inside. Look, it's more like a linear kind of relationship. Now it's not linear, but it looks on the graph more like a relationship. And then, so this is interesting. So again, we're not going to spend a lot of time on this, but you can start to draw your own conclusions. It's really interesting that the more money you make, the longer you live. Right? Isn't that what the conclusion that we would draw? And what's interesting, though, is, so, I don't know, 20 or 30 years ago, let's go back to 1980, like, look at that trend. It's incredible. You make less money, you don't live as long. You make more money, you live longer. Across the planet. It's pretty clear to me that there's a relationship there. But as the world like evolves and technology and we improve all kinds of technologies and education improves and stuff over the planet, you saw when we got closer to this year, everybody's life expectancy goes up. There's still a relationship, but more, regardless of how much money you make, life expectancy is more consistent. So if I just jump up to the end here, like it's not as big of a discrepancy, I think. Okay? And then if we go back even further, I don't know what's going to happen. Again, you see life expectancy is a lot lower, but the relationship is certainly there. The more money you make, the longer you live. Kind of interesting. Okay? But look at the scale now. So 400, 1,000, 2,000, 4,000, 10,000, 20,000, 40,000. The distance, the distance between like squares on the grid paper is not equal. It's not counting by ones or counting by 10,000s or whatever it was doing, right? Every time I go up a grid square, the amount that the grid is worth changes. So the first one's 1, the next one's 2, the next one's 4, the next one's 8, or whatever the scale is, right? And this is what we call a logarithmic scale. And this is huge. I mentioned this last week, that some of you that don't have as much of an interest in math, and you're taking this course because you need to, because of the program you want to go into says you need to have it, but you're going into some kind of social studies or social science kind of area, you'll do this. Like, you may not have to do the log laws that we've been working with and solving log equations by factoring the stuff that we've been doing, but you will be using logs as your scale. So you have to have some understanding of logarithms and why a logarithmic scale sometimes gives us a better feel for the data. If I go back to a logarithmic scale, you can see the curve. Now that we see that there is a trend, you can see that curve happening, right? But it's more obvious when I put it to a logarithmic scale and I get like a straight line. So it's not a linear relationship, as we would have explored in grade 9. On the graph, it looks linear, but the scale is not linear. So the relationship's not linear. But there certainly is a relationship. And what that means is it's not like for every dollar you make, you live another year. It's like the first dollar gets you a year, but then you got to make $10 to get the next year. Then you got to make $100 to get the next year, or something like that, right? Depending on how the scale works, if it's logarithmic one way or the other. That's the idea. So it's kind of interesting. Let's see what else we have. We're just going to look at a couple other examples. This is not something that you're going to be doing, obviously, but it's interesting to see the power of logarithms. So this one, right now, both of the scales are logarithmic. And look at that data. And this is child mortality and income per person. So what this is saying is the more money you make, the fewer child deaths, I suppose, in your family, of your children. So this is child mortality. 0 to 5 years, it's kind of morbid, I know, but 0 to 5-year-olds dying per 1,000 born. So for every 1,000 children born, by the time they're age 5, this is back in, looks like about, 1990, in China, because that's obviously China, about 50 children would die by the age of 5, and the income per person was under 2,000. So this is like every country, right? This is showing across different countries. But like, look at that relationship. It is so clear. And then if I change one of these from logarithmic to linear, it's more of a jumbled mess. You can see the curve. Once you know that there's a relationship, you look and see the curve. But really, there's nothing interesting going on here. This huddled part of the graph looks to me like no matter how much money you make, all these people look like they make about the same money, and the deaths are all over the place, from 50 up to 300. That's a pretty big difference for a bunch of countries that all make the same amount of money. So I'm not seeing a relationship there. But when I change it to logarithmic, I do. And then there you go. When both of them are linear, again, you can see the curve, but it's not as obvious exactly what the relationship is. Like, there's nothing up here.
Excuse me to interrupt.
So it's not random.
We're sending all students to class. They will not have a late slip for the next 10 minutes. Or no students can come to the office to get a late slip for the next 10 minutes.
Do you understand that there's nothing up here? Like, there's something going on, because it's all shoved in here and it's all shoved down there. But it's not exactly clear what the relationship is. And this is two graphs that are linear. But when I change them both to logarithmic, I get a really clear, nice relationship view of what's going on. Okay? And let's see. Oh, there was something that I forgot to mention in the last one that's interesting too. I'll go back. So here's where, this is back in the 1800s. Look at, it looks like in spite of how much money people made, child mortality was about the same. Over 300 by the age of 5 per 1,000. That's a lot. Sad, right? And then what happens over time is you can see them start to creep down. You're seeing like these other ones that are jumping up over, like out of the scale, right? They're appearing from above because they have more. And then look at this. As the world starts to get a little bit more industrialized and that sort of thing, and we learn about modern medicine and that sort of thing, all of a sudden, for a lot of these countries, and where are these countries? Well, orange is European countries. I wonder what that red one is. Somebody might be able to guess. And then there's the U.S. and there's Canada, right? Canada and U.S. Canada's always right there with the U.S., just sort of off its shoulder. It's interesting. And what are these green countries? It's interesting. You could play with this all day. So what is this? Saudi Arabia, Iran, Libya, Kuwait, Japan, of course, Sweden, Switzerland, Russia. Russia, interesting. Okay, all kinds of stuff going on there. And then what are these ones? All the African countries. All these blue dots up here are all the central and southern African countries. Mozambique, Malawi, Ethiopia, Mali, Nigeria, Tanzania. Interesting. Okay, what's the next one? This is CO2 emissions versus income per person. I'm just going to play it. It's two linear scales. Kind of looks like an interesting relationship there. And if I make it logarithmic on both sides, I don't know, like it's not about what's better either. Is that better? It actually is a tighter relationship there than it was before. The dots were a little bit more kind of spreading out, right? But it's kind of interesting. So the more money you make, the more emissions, right? That's what this is saying. Whoops. And look at China just like flying up from the back of the pack there. Okay, let's see what this one is. This one is math achievement and income per person. This website has a bunch that it's pre-made for you. So you can just click on them and it'll come up and it does all of the, like everything for you. It fixes all the stuff up for you to see the trend. And this one actually had something to do, you can see it up here, Asia is best in math. So it was like it was actually exploring the concept of the stereotype that Asians are good at math or Asian countries are good at math or whatever it is you want to say. But it kind of does look like, look at all 5 of the top dots are Asian countries. So it's kind of interesting. This is back, this is only 2007. If I go back further, it still kind of looks the same. There's Canada right there. We're really up there, but still far down. Who knows where this data comes from or what it's measured. There is a worldwide test called the Pisa Test. I think PISA, I think is what it is. Anyway, I don't know. Not as interesting. This is linear and linear. What if I change it to logarithmic? If it lets me. So with this website, there we go, logarithmic. Yeah, see, I don't know. Not necessarily helping. With this website, you can actually find the data as well. Somewhere, something that you click on will actually give you the data that is building this graph. So if you were doing a data management or some other project, world issues, if you're taking that course, something like that, could be a good resource. I just want to go back. Any questions about any of this? Just want to go back and play this one again. So I don't know if this is in the right. It's linear and linear. Let's go to logarithmic again. I think that's what it's supposed to be. And let's just play it and just watch what happens. So this is life expectancy. So we're at about 1900 now, 1910. Whoa, what just happened there? You see that? Interesting. Blip in the data. Whoop, go back. Do it again, kind of. Oh, like that. What's happening there? Yeah, the 2 world wars. Look at so the first one was World War I, the second one was World War II, exactly right in the early to mid 40s and right in the late teens of the 1900s. Like, look at the movement in the data. Shows you how many people across the planet, all countries everywhere, died during those times. Really quite crazy. Okay. Anyway, that's that. So, these little things that I've listed here are just a few things that you can explore, thinking about how the logarithmic scale, which is not what we're doing, we're going to use our understanding of logarithms and exponentials and stuff like that to solve some problems. That's what we're actually going to do. But there's this whole other application of logarithms in making a logarithmic scale that can be really important. If I look at this, does anybody have a pool? Anybody in here own a pool, a pool in their backyard, that kind of thing? Or maybe you've explored this in chemistry class, that kind of thing. The pH scale. Okay, so the pH scale is logarithmic. So if you have a pool, you often have to measure the levels in your pool, and you're measuring the pH, which is like a measurement of how much acidity is in it or not in it, or how much base or something along those lines, right? And so the higher the pH, but look what's happening. Okay, so what does that actually say? It says concentration of hydrogen ions compared to distilled water. So a pH of 0 is battery acid, very strong acid, and it has a lot of hydrogen ions compared to distilled water, and that's a pH of 0. So look what happens when I go up to 1, the scale is divided by 10. But then when I go up to 2, so that's a decrease of 9 million. When I go to 2, I'm not decreasing by 9 million again. That would be linear. Every time I go over 1, I go down 9 million. Over 1, down 9 million. Over 1, down 9 million. That would be your slope, your rate of change. That would be a linear graph. That's not what's happening. Over 1, down 9 million. Over 2, down 900,000. Over 3, down 9,000, right? Or 90,000. See, every time we go over 1, the scale changes. So that's a logarithmic scale. So pH is a logarithmic scale. And the thing that's strange about it, and there's a few other things in the world, famous things that are logarithmic, is that every time you change it 1, you think you're kind of changing the same amount, but you're actually not. You're changing by a different amount every time. So another example that you've probably heard is the Richter Scale, which actually they don't really use the Richter Scale anymore. They use a modified version of it. But anyway, they use the Richter Scale for some things. But this is we're going to pretend we still use the Richter Scale. This is what they use to measure the magnitude or intensity of earthquakes, right? So an earthquake that measures a 4 is not big.
Students, we are back to normal.
And then an earthquake that measures a 5 is quite a bit bigger. An earthquake that measures a 6 is quite a lot larger, but it's not the same measurement between a 4 and a 5. Like a 4 to a 5 wouldn't be that big of a difference, and then all of a sudden to a 6 is like huge, right? It starts to get, and then a 7 and an 8 are like disastrous, like they can destroy a country when you start getting up that big, right? And it's not like every time you go over 1 on the Richter scale, you're going up by the same amount. The change from a 6 to a 7 is drastically larger than the change from a 4 to a 5 because the scale is logarithmic. Okay, so that's really important to know. And the other thing is decibels. So we measure the intensity of sound or the loudness of sound in decibels. That's a common unit of measurement. And so these tables are not things obviously you have to memorize or write down. If you ever needed to use a table, I'd give it to you. So a soft whisper is a 30. Normal conversation is a 60. A rock concert is about 120. A jet engine, a space shuttle launch is 180 decibels. But here's the thing, like this is a change from 100 to 120 is a change of 20. But a screaming to rock concert and rock concert to jet engine, even though the decibels are changing by 20, the change in intensity is not the same. It's not an equal change between these two as it is between these two because of the logarithmic scale. And why do we do that? Because if we didn't, then the scale would be measured in thousands and millions. We'd start with like a 30 for a whisper, and by the time we got to space shuttle launch, it would be like 180 quadrillion or something like that, right? Like the numbers would get too big. So we use a logarithmic scale so the numbers are more familiar. That's why they do that. And I think understanding that is important. Like I think it's important when we do questions like this where we're comparing intensities that you understand that it's not a linear scale. But ultimately, we're going to do some problems where we're just kind of solving. There's sort of two, I would say there's sort of two different kinds of problems. Problems that are exponential and problems that are logarithmic. Okay, so by the end of tomorrow, you kind of need to have a good sense of how to do both. Does that make sense? Any questions? Okay, we're not going to start with that one. What one are we going to start with here? Let's start with, I want to start with, let's start with question number 5. It's kind of an easy one, but yeah, this is a good one to start. Question number 5. So again, you've got this on your handout. Don't try to write all that down. I think all of it is on your handout. Yeah. The remaining amount of a radioactive substance can be calculated with this formula. So take a look. M is the mass that's remaining after some allotted time. Okay? T is time. Where does it say? In hours, seconds, days, weeks, minutes, I don't know, like whatever it is, but T will be time. Okay? P is the original amount. We use different letters for this. Sometimes it's A, sometimes it's P. It could be all kinds of things. Okay, but this number that's multiplied out front is how much you start at. When we did exponential graphs, we saw that. Okay. I said T is time. I said M is M is mass. And H, what is H? H is the length of time where a half-life occurs. So if a half-life occurs every 3 weeks, T is time in weeks, and H is 3 for every 3 weeks. If a half-life occurs every 7 seconds, T will be time in seconds, and H will be 7. And you'll understand why in a moment when we look at this. Okay, so it's really important that you understand that the exponent is a fraction, the top is T, and the bottom is how long it takes a half-life to happen. This is something you need to know. Okay, you definitely need to know this formula. And half-life, what does half-life mean? Again, this is something that's like exponential or logarithmic, depending on how you want to think about it. They're related, right? Kind of the same idea, depending on which direction you're thinking about it. So what half-life means is after a specific amount of time, half of a substance will remain. So in the first 10 days, half of it's gone, which might be 100 grams. In the next 10 days, half of what remains is gone. So the first 10 days you lost 100, the next 10 days you only lose 50. The amount you lose changes, but every time it's a half, right? So it's a multiplier, so it's not linear again. It's a different kind of relationship. That's the idea of a half-life. I know you've seen this lots of times. You've explored this before. And this is how radioactive substances behave in the real world, which is very useful for all kinds of different things, dating really old things. And what I think is interesting is it's not like so let's say you literally have a rock of like beryllium 89. I don't even know if that's a thing, but let's say beryllium 89 is let's just pretend that it's a radioactive substance. I don't know. Okay. You have a rock of 100 grams of that substance. It's not like the rock disappears. It's not like it's like disappearing into thin air. But what's happening is like the particles or the ions, the charged nature of those particles changes. So it changes from beryllium to some other substance, another form of beryllium that's not radioactive, or even some other substance entirely. So half of the rock would be like a radioactive state of beryllium, and half of it would be something else, right? And so you can look at that rock and you see how much of it is one thing and how much of it is another. And if you know the half-life, you can calculate how long that rock has been sitting there. That's the idea behind radioactive dating, carbon dating, or that kind of thing, right? So it's not like it's gone. So if you start with 200 milligrams of something, you probably still have 200 milligrams. It's just only part of it is, in this case, arsenic that you started with. Does that make sense? Anyway, again, that's the real-life application. So we have an example here. Arsenic-74 is used to locate brain tumors. It has a half-life of 17.5 days. And we're going to suppose we start with 100 milligrams. How much is left after 35 days? So here's what we're going to do. The amount left at time t equals the amount we start with, which is 100. Okay, so we're starting with our givens here. The initial amount, or P at time 0, is 100. It's a half-life, so the multiplier is a half. Something else that we're going to explore is when we change the multiplier. So when we change the 1/2. And then my exponent, t is just always t, and divided by the amount of time it takes for 1 half-life to occur, which is 17.5 days. So h is 17.5. Those are our givens. Okay? And A is pretty easy. How much is left after 35 days? So M at 35 equals 100 times 1/2 to the 35 over 17.5. What do you know about the number 35? It's a multiple of 17.5. Okay, it's twice. So this is where I want you to really think. That means 35 over 17.5 is 2. So if you can calculate these exactly on a test or whatever, you should. Okay, if it works out nicely, that's what you should be doing. And so this equals, just watch for a minute, 100. What is 1/2 to the 2 mean? Go back to grade 9 when we first started exploring exponents. It means 1/2 times itself twice. I've got 2 half-lives. I'm taking 100 and I'm multiplying it by a half once to go to 50, and then I'm multiplying it by a half. I'm multiplying that by a half again to 25. So it's going to be 25. 2 half-lives. Okay? So in the first 17.5 days, it dropped by 50 milligrams. In the second 17.5, it only dropped 25. It dropped by less, but it was another half-life. So that's 25 milligrams. You certainly can use a calculator to calculate that as well, but in this case we didn't really need to. We could just think it through. And again, half-life is really interesting if I do a table of values. So at time 0, it's 100. I'm going to do 2 things. Number of half-lives. 0 half-lives is 100. 1 half-life is 50. 2 half-lives is 25. 3 half-lives is 12.5, and so on. But what's the time? 0, 17.5, 35. 35 plus 17.5 is that 52.5? Right? So the time is changing, but it's how many half-lives have happened that we're thinking through. What do you think about that? See the relationship there. You've done this before. You've seen this before in math last year and in other courses maybe. Any questions? Question B. So this is where it gets interesting. This is what you couldn't do last year. Actually, for this example, you could. So I take that back. Now it's giving me M. The amount remaining is 6.25. So I put in 6.25 equals 100 times 1/2 to the t over 17.5. So in this case, it works out nicely, and I don't have to use logarithms. If it didn't work out nicely, I would have to use logarithms to solve this. What I'm going to do first is take the 100 over and divide on the other side. 6.25 over 100. And in fact, I am going to use logs. I could express both sides as a power of a half, because if I take my calculator and I go 6.25 over 100, whoops, typo, I get 1 over 16, which I can express as a power of 2, right? But we're not going to do it that way. We're going to do it a different way. But you could. That would be fine to do it that way. I'm just going to show you how to use logs. Hey, Laf, you had your hand up? be a t. This t? That thing? It's not m times t. That's function notation. It's the mass at time t. That's what that means. Make sure you understand that because I don't want that to be unclear. We're using function notation. And in grade 12, that's how we start to do these. So it's basically m equals, but it means m at times t. It doesn't mean m times t. Does that make sense? Okay. So if I'm going to rewrite this in terms of logs, the base stays the same. Log base 1/2 of 6.25 over 100 equals t over 17.5. I can bring the 17.5 over and look, I've isolated t. Try punching that into your calculator. Either you can use the change of base formula, or if you have a calculator that can do it, you can just, so 17.5 times log base 0.5 of 6.25 divided by 100. Anybody do it? Talking days here. $70 I got. Try it yourself and see if you can get 70. Make sure you know how to use your calculator. Interpret that for me. 70 days, what does that mean? Very nice. If I go back up to my table, if I continue it, this with another 17.5 days, I'd be at 70. That'd be 4 half-lives, and that would be 6.25 milligrams remain. So we almost had it in our table, but there you go, right? So that was an exact number of half-lives set up to work out. So I could do that the grade 11 way by doing both sides as a power of 1/2, but logarithms can solve anything. That's what we couldn't do in grade 11. Grade 11 had to work out nicely, obviously not realistic, so it's nice to have a tool that can calculate exponents, this kind of thing, time exactly. Any questions about that? Okay, I'm going to jump to question 9. So this is one that's similar in that it's exponential. If we have time, we're going to do a logarithm one after this. I think we'll have time. But it's not a half-life. It's a different kind of multiplier. On bright sunny days, the amount of bromine in a municipal swimming pool decreases by 10% each hour. I'm assuming bromine is like something that helps clean the water, keep it safe, because public swimming pools are disgusting. So if there was 145 at noon on a sunny day, when would the pool contain 85? Okay, and it's each hour, each one. So the h, the thing on the bottom in the exponent, is going to be 1 because it's the multiplier happens each hour. Okay, but again, it looks like this. The amount is equal to the initial amount. Sometimes we use, again, I said these things change. So the initial amount times the multiplier. What should we use for multiplier? I'm going to use B to the T over H. What are my givens? The initial amount is 145. The amount that we're looking for is 85. The multiplier decreases by 10% each hour. So what's my multiplier? 0.9, thank you. right? So it's the amount that's left. It's not how much it's decreasing by. You subtract that from a whole. So it's like 100% minus 10%, or 1 minus 0.1. Either way, it's 0.9. That's the multiplier. I'm left with 90%, so that's what we multiply by to find the amount that's left. And h is 1, and t in this case is what we're looking for. So I'm actually going to write my equation. It's a equals 145 times 0.9 to the t. Right? So that's the equation in this case that relates a and t. This is part of this process, is developing the equation yourself. It's not going to give you the equation. Okay? And you have to know the different parts of the exponential equation. The fraction and the exponent to me is probably going to be the trickiest part. Figuring out the multiplier is also something that you probably want to think about. Okay, and then I sub in 85. And we solve. Again, bring the 145 over, so it's 85 over 145. Rewrite in logarithmic form, and I get t equals log base 0.9 of 85 over 145. If I want to use the change of base formula, does anybody remember that from a few days ago last week? It would look like this. I'm going to do log base 10. So I'm changing the base to 10 because that's what my calculator does more easily, of the argument over log base 10 of the base. You can try it both ways on your calculator if you have a calculator that does the fancy base. So log of 85 divided by 145, make sure you close your bracket if you have that kind of calculator, divided by log of 0.9. And I got 5. Interpret our answer, that's 5 hours. But the question said it started at noon. So at 5 p.m. There will be 85, what is it, grams, milligrams? What is this? Grams. Grams left at 5 p.m. It started at noon, so 5 meant 5, but be careful because it might not always, right? If it started at 9 in the morning or 7 in the morning when they open the pool or something like that, then you'd have to do that calculation, so be careful of that. Any questions? That's one type. Again, figuring out the multiplier. If it's increasing, here, take a look. Here's the trick. If it's a percentage increase or percentage decrease, it's 1 minus the multiplier or 1 plus the amount of the increase, right? Or 100% plus or 100% minus, however you think about it. But eventually, it's got to be as a decimal. You can't use the percentage in there. It can't be 90%, right? So 0.9, okay? If it's doubling, what's your multiplier? If it's doubling, Jason? 2, yeah. Okay, if there's no trick there, 2. It'd be 1 plus 100%, which is 200%, which is 2. If it's tripling, it's 3. If it's quadrupling, it's 4. If it's increasing by 50%, that's 1.5. If it's decreasing by half-life. If it's decreasing by 25%, your multiplier is 0.75. Do you see how this all works? So figuring out the multiplier is a tricky part. The fractional exponent can be a tricky part. And then you got to remember that equation and just know where to put the different parts in. Okay, let's go up and we're going to do question number 1. Wait, change my mind. We're going to do question number 7. All these questions that have to do with a logarithmic scale are all the same kind of question and they work out the same. Okay? Whether it's a decibel question, I don't think there are any in the homework today. Let me see. Or it's a earthquake question or anything like that. They're all kind of the same. Okay? On your handout, right above question number 3, gives you the equation for an earthquake for a Richter scale, and it looks like this. It's log of A over T plus B. But it turns out the T and the B are basically irrelevant. You're going to see them come out in the wash. We're going to start with this equation anyway. And again, I'll give you these equations. I don't expect you to memorize them. Every equation basically looks like this. Log of something over something. Okay? And there might be other junk involved as well. But they basically all look something like that. The plus B is going to be irrelevant. So we don't care what it is. It's a constant. Same with T. We don't care what it is. We're going to do the algebra and we're going to see it is going to disappear. Okay, but we'll start with it in there. I think it's helpful to start with the equation as it actually is. So what this is saying is the Richter scale is a number. You're familiar with the Richter scale. 4, 5, 6, 7, 8, 9, whatever it is. An earthquake of 9 is like, it's only happened like 10 times on the planet or something like that, and it's like catastrophic. Like a 9 is insane. But an 8 is huge, like the Haiti earthquake that happened a long time ago that basically destroyed that country for years to come. They're still rebuilding from it. I think was like an 8 something. Okay. Oh, it's on here. Is it on here? Or maybe that's a different question. So even a 7 is quite large. A 6 is something that you would very much feel. Okay. So in this case, an earthquake in China registered 8.6. An earthquake in northern Peru, 7.7. How much stronger was the Chinese earthquake than the Peruvian one? It looks like only about 1 Richter scale more. 7.7 to 8.6 is a 0.9 difference. But that's not telling us the difference in intensity. So A is actually the amplitude of the ground. It's like you know how sine curves, cosine curves, trig curves have an amplitude. So the change in the amplitude of the ground. That's strange to think about, the ground moving, but that's what an earthquake is, but the amplitude of the ground. Okay, so how much the ground is moving in one compared to the other. That's what the A stands for, I think. But that's what we're exploring, is the A. We want to see the difference in the A values. Okay, so this is how I'm going to do it. I'm going to do China over here. And the Richter scale was 8.6 equals log of A over T plus B. And I'm going to do Peru, northern Peru over here. And that's going to be 7.7 equals log of A over T plus B. And what I'm going to do is I'm going to rewrite both of these in terms of A and then compare their intensities. Okay? The logarithmic Richter scale is designed for our comfort, so we can count 4, 5, 6, 7, 8. It's not a useful scale for comparing the actual values. Same for decibels, same for pH, same for any of those kinds of questions. So this is going to be 8.6 minus B equals log of A over T. And I'm going to rewrite this. A over T equals the base 10 to the exponent 8.6 minus B. And so A equals, see how, I know this is kind of funky, but I'm rewriting this in terms of A, and there's all this other junk involved, but it always just works out. Okay, so this is A. I'm going to put a little C, subscript C, for the amplitude or the intensity of China. And then for this one, it's going to work out exactly the same. 7.7 minus B equals log of A over T and A over T. So A of Peru equals 10 to the 7.7 minus, B. And the amplitude of Peru, or the intensity of Peru, is T times 10 to the 7.7 minus B. And then I'm going to compare. We only have a couple minutes left, so I know I'm going kind of fast, but these questions are very formulaic. They're the same every time. Okay? How many times bigger? In other words, I'm dividing. Okay? So this is going to be the amplitude of China divided by the amplitude of Peru. So it's T times 10 to the 8.6 minus B over T times 10 to the 7.7 minus B. Is everybody okay with that? I know I kind of went through that quickly, but are you okay with how we did that? We just rewrote in terms of the thing that's the intensity, which is always that top value. And then what happens? Oh, look, that constant of T is gone. And how do I divide powers of the same base? Subtract the exponent. So this is 10 to the exponent 8.6 minus B minus 7.7 minus B, which is 10 to the 8.6 minus 7.7 minus B plus B. So look at that. They're gone as well. That happens every time. We don't need to worry about those. What is 8.6 minus 7.7? 0.9. What is 10 to the 0.9? Folks, the 0.9 was the difference between the two Richter scale values, right? But it's not 0.9 times bigger. It's 10 to the 0.9 times larger. What is 10 to the 0.9? 7.9. So an earthquake of 8.6 is almost 8 times larger or more intense, 8 times larger than 7.7. Not 0.9 larger. Everything we talked about, all that stuff where we were exploring those graphs at the beginning, see how the logarithmic scale works. 8 times the intensity. That's crazy, right? And if I went from 8.8 to 9.8, 9.8 has never even happened since we've been measuring these things. It's bigger than the biggest ever. The biggest ever is like 9.5, 9.6. I don't even think they know exactly how big it was. If I went up to that, it would be like 10 times larger again. Like not a little bit more, even way more. Any questions?